Good afternoon. My name is Randy Stott, and I'm the managing editor of Gear Technology and Power Transmission Engineering magazines. And I'd like to welcome you all here to Ask the Expert Live. Today's topic is gear design, and I've got some experts here to answer your questions if you've got them. And I'm going to ask each of the gentlemen here to introduce himself, and then we'll get started with some questions.
So my name is Karsten Stahl. I'm head of the Gear Research Center at the Technical University of Munich. At our institute, we do investigations on gears, on all interesting aspects, gear strength, endurance, the noise behavior, NVH, and efficiency.
Frank?
I'm Frank Uherek. I'm principal engineer with the Rexnord Gear Group in Milwaukee. I've been doing gear design since 1980. I've got gears anywhere from something you can hold in your hand to something that weighs 220 tons, about 13 meters in diameter. I also have the honor and privilege of being the chairman of the American Gear Manufacturers Association Helical Gear Rating Committee.
Thank you, Frank. Chuck?
Chuck Schultz. I'm the chief engineer at Beyta Gear Service, a consulting firm. I've been involved with the gear business since 1971. Frank's probably got a little bigger gears than me, but I may have more gearboxes than he did. I've well over 600 custom gearboxes that I've designed and built. And I'm also privileged to be a member of his committee and Gear Technology Magazine's corporate blogger.
Thank you, gentlemen. I'm going to get started right in with the questions. And the first one I have is, how do you avoid gear pitting? Who wants to jump in?
Well, it's one of the reasons that we have rating standards is that we have a whole protocol, which is basically our understanding of what makes gears pit and what makes gears break, that we've collected over the 100+ years of AGMA history. And if your gears are properly designed according to that, our standards, we believe that they'll give a proper service life based upon the hours that you've designed. However, the things that interfere turn out to be lack of lubrication, poor lubrication, lack of maintenance, and poor application of the particular gearbox design. So the collected knowledge is in that standard. If you apply it properly and the gearboxes are properly maintained, we think you have a very good chance of avoiding pitting failures.
One of the other things that I always like to point out is gears never die a natural death. It's usually the gear problem is not connected to the design. It's going to be connected either to the application or the maintenance. And I have run into more problems with people bringing gears into service and not really understanding what is the load spectrum, what is the overload possibilities, and yes, they do actually have to change the oil occasionally. And a good oil monitoring program will keep gears going for years. And you've got to take care of them, and they'll do wonders.
Karsten?
Maybe a general approach. A damage occurs if the occurring stress is higher than the endurable or the permissible stress. So in case of pittings, which is one out of many possible damages of a gear, it's the Hertzian stress. So everything which reduces the Hertzian stress will reduce the risk of pitting, and everything which increases the allowable stress for Hertzian stress will also reduce the risk of pitting damage.
Just one last thing. One of the first paper that I ever did for an AGMA Fall Technical Meeting back in 1999, I went through 15 years of records of our gearbox rebuilding operation for cause of failure. And of the, I believe, over 1,000 gearboxes in that database, less than 10% of them failed because of design issues. 90% of them failed because of poor maintenance, contaminated lubrication, lack of lubrication. And the design specifications that have been developed by the collection of experts over the years is really very good.
Very good. Thank you, gentlemen. Next question I have from the readers is, what are the main causes of tooth interior fatigue fracture, and what can be done from a design standpoint to prevent it?
Maybe I start on that. It's the same as with pitting. A damage occurs when the occurring stress is above the allowable stress. So in interior fracture, it's the same. If the local stress underneath the surface is above the allowable stress, which includes the residual stresses, shearing stresses, and all the super layer of the occurring stresses, then a damage may occur. So in case of pitting, we have countermeasures. In case of tooth fracture, tooth root breakage, we have countermeasures, which all lead to stresses increase underneath the structure, underneath the surface. For example, shot peening increases the allowable stress on the surface, but not far below the surface. So especially for large gears and highly hardened gears, we have the increased risk within the last 10, 15, 20 years where we see damages below the surface, and we call it flank fracture, because the damage does not occur in the tooth root, not on the surface of the flank, but it is a fracture underneath the surface within the middle of the flank. And we are just in progress of getting a standard calculation in the ISO system 6336, where we define the calculation method to be used as a technical report.
And one of the items that you also have to consider with that particular failure mode is looking at the control that you have in your heat treat operation, making sure that the case depth is of sufficient depth, and again, having a clear understanding of the loading on that gear set. Mm-hmm. Because if you design it for load A and you overload it, you're going to get a surprise.
Yeah. We've had a lot of experience and a lot of years working on pitting and tooth breakage failures. This is basically the interior failure is an emerging area of concern that we know some things, but we don't know as much about these failures as we do about pitting and tooth breakage failures. So it's an area that a lot of research is going to go into. A lot of people will be looking at their failure analysis differently to try to find evidence of this so that we can begin to find solutions for it. It is believed that it's related to heat treat quality and also material quality, in that we know that steels with defects in them are more likely to cause this type of failure and to react poorly in heat treating. So this is something for you gear geeks to watch in coming years for more information on this failure.
Thank you, gentlemen. Next question is, how is profile shift used to optimize a gear design? Jump right in.
Carefully.
There are any number of papers out there and different methods of optimizing rack offset, which is also a term for profile shift. You'll see some people call it X factor. There's a number of different ways to calculate it. You can get into a lot of different minutiae about what you're doing when you're doing a rack offset. The traditional American term for it was long and short addendum, which caused more confusion than just rack offset as a terminology. But basically what you're doing is you're changing the outside diameters of the gears to change the shape of the teeth. As the rack offset becomes more positive, the tooth becomes broader at the base and narrower at the top, and the actual operating pressure angle increases. If you make rack offset negative, the tooth becomes skinnier at the bottom, and the active profile angle changes to a lower number. So you're basically adjusting the tooth thickness and the pressure angle, which changes the bending strength and changes how the action on the tooth occurs.
There is an AGMA information sheet which discusses how to deal with profile shift coefficients. Highly recommend you take a look at it. It is very commonly used in European gear design. It is very uncommonly used in America. And not because it's different or doesn't work. It works wonderfully. It's just something that Americans have not been used to doing it, and the Europeans have done extensive work on it, and it makes a significant difference. You always, when you're looking at a gear and a gear application, you want to make sure not only that it has sufficient power capacity, you also want to understand how it's going to fail. Because you don't want the thing to fail inconveniently. Now, I don't mean inconveniently at 10 a.m. on Friday morning when everyone's running out for the weekend, but in case of you want to have a benign failure, perhaps you want to have pitting before you have tooth breakage. Because a pitting set you can catch and you can look at and say, oh, okay, I've got a problem. I've either got to look at my lubricant or get a spare on order. Tooth breakage, gearboxes tend to fail the ratio test at that point, which is when you spin the input shaft, the output shaft don't turn. So profile shift is one of the ways to look at that, and the European rating standard ISO 6336 has a lot of influence factors which are driven by that value.
I would like to add that the base diameter shape is not affected by the profile shift. So what you can do with the profile shift, you can adjust the properties of the tooth, as Chuck explained. So what usually the gear designer has to do is play with this value, play and calculate. The trochoid is changing, so the stress in the tooth root is changing. The angle of the tooth force is changing, therefore the stresses and the curvature is changing. So play with it a little bit and see what happens, and you can balance the safety factors for tooth root stress and flank stress, and you can achieve exactly what you explained. You can balance if you accept pitting on a higher level and no tooth root breakage at all. You can do that easily with the same tool, just changing the addendum factor.
I rarely disagree with my friend Frank.
But then don't do it
But
now.
rack offset as long and short addendum has a long history in American gearing. And it's been used to solve problems. One of the problems we frequently encounter is undercutting. If we get to low numbers of teeth, we have an undercutting problem on the root fillet area. If we increase the rack offset, we bring that root diameter up and we change the shape of the tooth, and the undercutting goes away. We also use it to adjust the strength between the parts. I started using it about 1975 by accident. I had a project and we had some goals from our marketing department that we were supposed to meet, and we weren't meeting them. And we were slaving away at our computer, punching our cards, running them through the computer. And one day, a problem that had resisted resolution for a long time suddenly solved itself. How did this happen? Well, my fat fingers transposed the outside diameter on the pinion. And in doing so, I enlarged the pinion more than the family recipe called for. And suddenly, what was a limitation on the gearbox capacity went away. I started saying, well, maybe I can do this on some of my other problem spots. I resolved the problems, and I immediately got hauled into the boss's office because I must be doing something wrong, that I made my problems go away and the other people on the team didn't make theirs go away. Large investigation ensues. We discover, hey, if you play with the outside diameter of the pinion, you can make some of these problems go away. Now, you might have created some other problems, but at the time, we got marketing off our back.
Thank you, gentlemen. My next question comes from the readers, and it says, how do I ensure that the right lubricant is specified to match my gear design?
Well, your first source of information for that is the manufacturer's operatings and maintenance manuals. Wherever you bought the gear set from or the gear drive from, they're going to have a list of recommended lubricants as a function of ambient temperature, as a function of viscosity needs, as a function of auxiliary equipment in the gearbox, such as a backstop, that will drive a proper selection. Unfortunately, in most cases, your receiving department will discard that information immediately while unpacking the gearbox. So if you can't, then go to the manufacturer's website, obviously, and go from there. If you can't get that, AGMA has an excellent publication called AGMA 9005, Industrial Gear Lubrication. And that lists a series of performance criteria that various types of lubricants, such as mineral oils, such as synthetics, anti-wear, anti-scuff oils that need to meet, that will run in very general applications. And that will also allow you to make sure that the lubricant that you're getting from your lubricant supplier is of sufficient quality and of sufficient additive package to keep your gears happy. So again, manufacturer's website, first spot, second spot, AGMA 9005.
I think it's a danger and a problem if you design your gear and at the end go to an oil supplier and buy a lubrication. Lubrication is part of the design process of any gearbox. So at the beginning you have to decide for a lubrication. It's dependent on the time of life for the base oil, the range of temperatures, the friction, the coefficient of friction, the additives you put in, the corrosion and the behavior with colors and paints and copper. So many things to consider, and you need to do that in the very beginning. Then you have the input data for film thickness and other stress relevant data to define and calculate the stress and the safety factors for scuffing and micro pitting and pitting. And then you can find the balance, for example, using the shift, the profile shift, or other geometry sizes and factors. So this is my hint to every user. Put that the selection of lubrication in the beginning and not in the end.
This is an area where the bearing people are way ahead of us for once. They have an environmental factor, A23, that they use, which calculates the effect of lubrication conditions on the bearing life. And I believe over time we will move towards a similar system for gears, because there has to be a connection between not just the loading of the gears, but the rotational speed, the surface finish of the gears, the actual geometry of the gears. And this is one of those areas where we've gotten away with ignoring it for probably as long as we can. And we're probably the next generation of standards, after Frank and I have retired, will need to start looking at the connection between these things and the gear rating in life.
Thank you, guys. Next question is a little bit philosophical, so bear with me here. Have we reached the limits of gear design for today's materials, or are there still things we can do to increase load carrying capacity? What are my options?
May I start?
Sure.
I think today it's not about gear strength as a singular property of the gear. It's always a game of strength, efficiency, and NVH behavior. And we will not expect a major step forward in strength or in any other property. I think what we are achieving on a year-to-year basis by research and the work of all the engineers in the world is coming closer to the limits. So stepping a little bit up to how can I calculate the strength a little bit more defined without losing efficiency or NVH behavior. How can I find the better balance between efficiency and strength? There are so many values in the transmission affecting both, and the more accurate you can calculate, the better you can find the optimum. And it's not one optimum for both, it's a balance. And I think there's still a lot of room to optimize one gear set to the specific application. When the customer exactly knows what he wants, that he exactly gets what he wants.
Yeah, I think in the beginning when gear standards were developed, the favorite factor they had in them was one. We knew that size was a problem, but we didn't know how big of a tooth affects the rating, so we said, well, the size factor is going to be 1. We knew surface finish was a factor in rating. We didn't know really how that affected it, so we just put a 1 there. And we basically put out a group of sign points that said, hey, these are areas that are going to affect gear rating. And now through the technology, we have gotten smarter about surface finish. We've gotten smarter about material quality. You know, in the ancient days, you know, we would add sulfur to steel because it was easy to machine. Well, it also wrecks your steel from a stress standpoint. Well, why did we do that? Well, we did that because we didn't know and we couldn't get the sulfur out of the steel. Now we can get the sulfur out of the steel and we have carbide tools so we can cut the teeth better. So we've gained another bit of rating. It's, as it was said, we're not going to have a breakthrough jump of rating of 20 to 30%. We're going to have breakthroughs of 1%, 2%, 3% around the area. And we're just approaching and understanding more and more factors. And as we get a better handle on factors and loads, we can incrementally increase ratings. So yes, power capacity is still available.
I'm more optimistic than either of you. 96 years ago, we standardized on a tooth form with an addendum of 1 divided by the normal diametral pitch. That's not the only tooth form that you can have. I became intrigued with high contact ratio gears. Most automotive and motorcycle gears are now high contact ratio. 96 years from now, if we've invested that time wisely in learning about other tooth forms, we may discover a whole new realm of capacity. Plus, there's things to think about now, just with the tools that we do understand. If you were to take a couple of different automotive transmissions apart and lay the parts out, you would see parts that looked exactly the same, are very similar in size, and one of them is in a 100 horsepower economy car, and on the other side is a 1,000 horsepower Formula One car. And the parts are similar in size. They're all made out of steel. They're all heat treated. But the performance levels are entirely different. What you're going to be seeing is more of that high technology, the lower price point. And we have a lot to learn about many things about gears, despite several thousand years of the smartest people in the world working on them.
I think you're right in this quality and quality versus cost issue. We have a scatter. If you have a strength of a gear, it means there is one very strong gear, one very weak gear, and all the other gears are somewhere in between. And the more accurate we can produce and the more accurate we can calculate, the more we can lower the bottom. So our target value becomes higher. So therefore, we will not improve the best gear from 20 years ago, probably by far, but we will definitely improve the worst gear from the past, and therefore lift the whole average.
The other areas that we have open to us for improving performance are improving the maintenance, the predictive maintenance aspect of things, and also controls and operator abuse. Back when I was involved with making parts for a world-famous racing team, they had chronic transmission failures with one driver, and the other driver never had any problems. And they were exactly the same parts, despite the driver with the problems insisting that he was getting all the junk parts. And it was all due to operator abuse.
We have a question from the audience.
This is another philosophical question. I'm fascinated by this dynamic about the poor maintenance and whatnot that still exists. And maybe this is more a question for Sigmund Freud, but how do you account for that behavior by American companies? And is that more endemic to the United States, or is it also a problem in Europe? Is it also a problem in Europe and throughout, or is it an American thing? I think if somebody wants to find insanity is repeating the same thing over again and expecting a different outcome. It's kind of hard to believe that they know what the result is going to be of not, keeping up the maintenance, and yet it's like, so what?
At the risk of using up several months worth of blog post ideas, I put it to you this way. In a group of people with your automobiles, there's going to be a group of people that keep track of every gallon of gasoline they put in the car. They religiously follow the manufacturer's maintenance records. They're over getting their oil changed every 3 months. They keep the air up in their tires because that's the way they are. Then there are the people that treat every car like it's a rented mule, and they really don't care. There's a growing feeling in some sectors that run to failure is a perfectly acceptable shop maintenance practice. There are other people who feel every machine should be treated with reverence, respect, and love, and kept as clean and as well maintained as possible. And it's interesting to see how that plays out, but in many cases, people don't have a choice. I've been in steel mills where, frankly, it'd be amazing if someone could get in and change the oil. Simply because you got gearboxes stacked on top of other gearboxes, and you just can't get to it. A lot of it has to do with the individual circumstances. We as engineers would love everyone to be treating our products with reverence, but they're not. And they're never going to.
I think predictive maintenance and condition monitoring systems will help there. You can increase or reduce the safety factors on gears. If you have condition monitoring, a flag goes up, this transmission has to be changed. And if you change 1 out of 1,000 transmissions and increase the density, the power density, it will be a positive business case. So with all the sensor potential we have with modern vehicles, modern powertrains, I think there is potential to accept that some of the powertrain parts, like gears, have to be changed for special drivers, special situations, or bad luck, or accidents. And then you can raise all the rest, the soft drivers and the lucky ones.
Frank mentioned oil monitoring, and one of the things that I've encouraged my clients to do is to engage in a scientific oil monitoring system check. Particularly our European friends, where they limit the amount of hydrocarbons you can have in a facility, and you pay a steep price for disposing of used product. People have made great strides and improved their reliability by engaging in a program of monitoring the lubricant, filtering out the contaminants, and restoring the additive package while leaving the base oil in place. And this is an area that maybe the oil companies don't necessarily want to encourage because they make money selling barrels and barrels of oil, but it is certainly an area that I think environmentally conscious companies and cost-conscious companies are going to start looking at.
And the other item to the audience's question is the experienced mechanic is probably not there anymore. The guy who just grew up with grease and oil and fingernails every day and could walk by a gearbox and put a screwdriver on it and say, I think the high-speed bearing's about to go. Those people don't exist anymore. But what does exist is, the industrial Internet of Things. Instrument your gearbox, do vibration monitoring, temperature monitoring, oil quality monitoring, and then they can sit in front of the computer and, oh, conveyor number 4 has got a hot bearing. Let's go and replace it. And do it in an economical manner, not at the last day of the month when you're trying to ship everything, that half your production line goes down. So I think with sensors and so forth, the gearboxes will once again be treated with reverence.
Yes, as they should be.
Yes.
Thank you, guys. Next question. How can I tell if my gear design will suffer from excessive whine? I'm especially concerned about noise in the higher order harmonics. Anyone?
I can start answering this question. So gear design, microgeometry and macrogeometry will result in transmission error, more or less. You never have conjugate gears where when you rotate one gear, the other gear perfectly follows. You always will have a transmission error. For example, if you want to have a good behavior of the teeth, you put a crowning, a tip relief on the gear, which results in a transmission error under variable loads. And the answer on that is you have a choice of programs to calculate. So there are many simulation programs. Of course, we at Technical University Munich have a program which is called DZB, where you can put in the nominal data, or you can also measure your gear with all the pitch errors and lead errors, and let the program calculate the transmission error under load, and also the dynamic transmission error under load and speed. And then you can run an FFT, a fast Fourier transformation, which gives you the answer on which order comes with which level in the incitation. What results then in noise depends on the whole powertrain. This is very complicated. So in a car, you don't hear the gear, you hear the dynamic force transmitted through several paths, and then maybe you hear something in the car which starts to vibrate of that. So what is true for any case, 1 decibel reduction in the dynamic force gives you 1 decibel reduction of the airborne noise in your ear. Mm-hmm. So this is what you want. You want to calculate the noise level of the force, and then you can assess and improve this behavior.
Okay.
I mean, the other issue that you want to look at, in addition to taking your design and going through the analytics, is also build the system and do actual noise measurement, vibration measurement testing. Because as was stated, it's not only the geometry of the gear set, it's also the housing, the foundation, and the surrounding items. And it also surprisingly depends on what the gear set is doing. If you are crushing rocks, I don't care about whine, because I'm not going to hear whining, I'm going to hear rock crushing. If I'm in an operating theater and I'm trying to raise an operating table for the surgeon, I don't want any whine there. And the combination of analytical software, microgeometry modifications, fine pitch, high numbers of teeth, will tend to manage your noise problem appropriately.
We've come a long way from the days when we used to tell people that singing gears were happy gears. And the analytics have certainly helped. Generally speaking, if you follow the design procedures that are used, and the gears are made without excessive manufacturing defects, you'll get a pretty good performance. But our ability to predict from the mathematics what the actual gears are going to sound like is still rather limited. So you can follow the recipe as well as you can. You're still going to have to build some parts. And once you've got the parts built, there's a lot of tools available to help you modify the sound output from those gearboxes. But short of actually building the gearboxes and the environment they go in, you're not going to get an accurate prediction out of the noise unless you're at the very highest level of the science.
Part of me says yes. Some other part says if you take a lot of effort in the calculation, in preparing the data and putting up the model, it will be more efficient to build it actually and to measure. If you think of big gears or one-off, a turbine with 100 megawatts, you do not want to build a sample and hear. So you will have to put a lot of effort in simulation and calculation. It's worth it. So I think the answer is both. It depends on volume and size and cost for prototypes, whether you make more experiment or more calculation. Both is available.
Very good, thank you. Next question. How can gear designers take advantage of recent advances in machine tool controls to optimize their designs for a given application?
It's a slippery slope. Just because you can do something doesn't necessarily mean you're smart enough to do it. A lot of people are overly fond of microgeometry modifications, in my opinion. When you think you're optimizing microgeometry, you are optimizing it for one particular set of loads. And if you encounter loads different than that in the field, you are by definition sub-optimized. So you can use all those tools about putting a tapered lead crown on, putting tip relief on, putting root relief on, putting all kinds of fancy modifications on the gear teeth, but they may or may not solve the problem that you're trying to solve.
Yes and no.
Okay.
I mean, part of the problem is if you just take a unmodified profile or unmodified helix, and then you rate it to an AGMA gear rating standard, and you're using high quality grade 2 material, you're going to have a failure. Because those standards assume some sort of microgeometry modification. Now, the next step of that, when you're looking at that, we say, well, have your leads been properly modified? And the people who wrote the standard are very smart. They don't define what properly modified actually means. They just said, did you do it correctly? And if you didn't do it correctly, you're going to end up with a gear set that instead of having 5 inches of face in contact of a 5-inch wide face width, you'll have one that's 2 inches in contact because you've overcrowned it. Or you'll have tip to root interference. The advances in machine tools allows us to fine-tune microgeometry. And if you know what your load is, and if it's a steady load, you can optimize. But you can also say, well, gee, I really don't know what my load is. I'm going to have some variation. You then optimize for what you think the load is, and then check the extremes to make sure you haven't absolutely sub-optimized the issue. So from the standpoint of machine tooling, we can go and can put in a tapered lead to deal with torsional windup, and crowning to deal with bending deflection, and tip relief on the profile and root relief so we can conquer whining and other noise issues. But as Chuck has said, you have to know that initial load. If you don't know what that load is, you're just fooping in the wind.
I would like to add two things. One is manufacturing must be in balance with simulation and program tools. So in the past, 50 years ago, we had a thumb rule what the tip relief should be, length and profile-wise. Today we have sophisticated tools to calculate 0.5 micron exactly what crowning and topological modification you need. So therefore you need machines being capable of producing that. So one without the other does not make any sense. So if you have machines being capable of tolerances within the micron or even less, that helps you to define modifications in that range. Second, all the engineers are dreaming of a load-independent modification, and we are working on it. and I'm pretty sure that there's a way. So let me easily explain how the idea behind that is. If you have the plane of action, the tooth plane, what we are doing is we take a part of that and put a periodic modification on it, and the size of this modification is dependent on the load. So the higher the load, the more this part of the flank is engaged, and therefore you have a factor now. So the impact of this periodic modification is dependent on the load. So therefore you have an adjust key to more or less let the periodic modification have an impact. And there is light at the end of the tunnel that we will be able to calculate, and maybe some years later even to being able to reproduce this on machines.
How far away from that are we?
In theory, in prototypes, we are very close. So we are able to have periodic modifications which are far better than topological modifications, but not for all loads. So I think in 5 years maybe we can do that in prototypes. Maybe in additional 2-3 years we can do that in serial production.
Very interesting, thank you.
Okay. We probably need to warn about misapplication of family recipes, though. One of our committee members published a wonderful paper on noise complaints in diesel engines. They were getting customer complaints and warranty returns on diesel engines that were deemed noisy in the timing gears. So they set up a nice experiment. They asked for 5 bobs, the best of the best, and 5 wows, the worst of the worst, I love those terms, from the test line. They took the gears out of them and looked at them, and the wows actually had gears that checked closer to the drawing parameters than the bobs did. And after much investigation, they discovered that the manufacturing people had properly applied the family recipe for tooth modification to the gears. However, the gears were not conventional addendum gears. They were high contact ratio gears. So what they had done is they had put a tooth modification that was halfway down the tip of the tooth and took away much of the high contact ratio advantage. So the wows, which were closer to perfect according to the drawing, were worse performing than the bobs, which were almost ready to fail according to the drawing because they didn't have enough tip relief on them. And when they took all the tip relief off them, all the engines became better than bobs. So rules of thumb and family recipes are wonderful, but you have to understand their application and make sure that you aren't stretching them a little too far and in the wrong direction.
Thank you, guys. Moving on to the next question, and I'm going to remind the audience, if you have questions for the experts, you're welcome to raise your hand and we'll give you a microphone. What are the advantages and disadvantages of increased pressure angle?
Well, pressure angle in the deep dark past in the early 1900s was 14.5 degrees. And at that time we had pinions that were populated with many teeth, and it worked well, but it really didn't have a great strength rating. So then we slowly moved to 20-degree pressure angle, and we got a little more strength, and gears got a little noisier. And then we moved to 25-degree pressure angle, and that's basically where most of the industry is around at this point. We're somewhere between a 20 and a 25, and if you're running with profile modifications, you might get above that. As you get larger in pressure angle, you are making a wider base to your tooth, but if the base of a tooth is getting wide, the tip of the tooth is getting narrower and narrower. And since most gears are surface hardened, as the tooth gets narrower and narrower near the top, well, the carbon, if you carburize, the carbon's coming in from the top, and it's coming in from the side, it's coming in from the other side, and you get a tip of a tooth that is incredibly over-carburized. And usually when teeth are over-carburized and you hit them, they fly off, which is inconvenient because it'll usually go through a bearing or go through a thing, and then our service department gets a phone call, usually at Friday at 4:30. So there is an upper limit to pressure angle. If you've been at the recent AGMA Fall Technical meeting, has presented a couple of papers on increasing pressure angle, and if you can deal with that tip disappearing, you can sometimes get a little more strength. However, you have to start now worrying about undercut, and you have to start worrying about numbers of teeth, because the formulas just don't allow that type of geometry.
You also start worrying about contact ratio. A conventional set of spur gears has a profile contact ratio of somewhere between 1.3, 1.5, which means that 30 to 50% of the time, two teeth are in contact. As the pressure angle increases, and again going back to our rack offset argument, as rack offset increases, the profile contact ratio starts to fall off. And once you get down much below 1.3, the operation tends to feel what most mechanics would say is very toothy, and tends to start loading the tips of the tooth more, which contributes to the tooth breakage issue that Frank was saying. Again, as an advocate for high contact ratio gears, the 14.5 degree pressure angle actually resulted in a lot of gears back in the olden days that had a profile contact ratio of over 2. And the noise that we frequently hear in gears is the switch of one tooth load to two tooth load, one tooth load, two tooth load. If you always have two teeth in load, you don't get that sound change. We also found that it's kind of like when you build a deck. You can build a deck with 24 inches on center, 16 inches on center, 12 inches on center, depending upon the closer the span is, the more likely your guest is to be on two joists instead of one, and it'll be a lot stiffer and stronger deck. And the same thing happens with gear teeth. One of the advantages that we see in high contact ratio gears is that we don't see a single tooth loading. So we want to be careful of our pressure angle selection and matching it to the operating conditions that we're looking for, and making sure that we have adequate profile contact ratio for the operation.
At FZG, we did several investigations with another aspect, low loss gears. So the loss is a function of friction and speed. And the higher the distance from the mesh point, the higher the speed. So a recipe for low loss gears is to reduce the height, going down below 1 with a contact ratio. So 0.7, for example, to reduce losses. Then you need helical gears with strong helical angle to compensate, to get an acceptable acoustic behavior. And what happens if you have small teeth? You can increase the pressure angle. And increasing the pressure angle to 35 or even more means the curvature, the radius of curvature getting larger. Therefore, Hertzian stress going down, Hertz stress going down means the coefficient of friction goes down. So again, power loss goes down. What we could show is with such a low loss gear, you can reduce the load dependent friction by 70% dramatically. But of course you have to compensate for strength and for noise. So this is my point from the beginning. It's always a
There's
game.
never one right
Yes.
answer.
You can make one aspect extreme, very good, but then you lose properties on the other two aspects.
All right. I think we have time for at least one more question here. This one's a little bit in depth, so I'll read through it and you guys can give me your best response. From a practical gear design point of view, how does one choose between a proper happy medium? Utilizing conventional standard gears and their inherent modest performance characteristics, for example, size, weight, load carrying capacity, noise and vibrations, etc., and low cost, completely non-standard, deeply optimized high-performance gear solutions with increased cost and development time, custom tooling, etc. How do you choose?
I can start this point. I think if you go to a specific application, not off the shelf, specific application with a customer with clear demands on strength, efficiency and noise, you have to use sophisticated tools anyway. So you you lose the standard. You have freedom in choosing the height, the addendum modification or the rack position, the angles and the helical angle. I think there is no other way but sophisticated, leave the standard, use whatever improves your individual property. When you calculate with sophisticated tools, you can optimize a gear much better than sticking to the standard tooth rack profile.
The other consideration that you have to give in trying to determine what is the best gear design is the application itself. What are you going to ask that gear set to do? And how much are you willing to pay? Because doing a highly customized solution will get you an optimal gear. However, you may not wish to pay $80,000 for that optimal gear. And you may not want to wait 18, 20, 26 weeks for its delivery. So then what you have to do is say, okay, I really know my loads. Loading is paramount. And then say, well, I can't do custom, but let's use all those sophisticated tools to say, out of the stack of gears I've got, what is the best one that matches cost, delivery, manufacturability, material availability to satisfy the constraints.
We're blessed to live in a time when we can make the best gears that have ever been made. The question is, how good a gear do you need? And we all have to make economic choices and style choices in all areas of our lives. Some people are perfectly happy living on cheeseburgers and French fries. Other people want fancy restaurant food. They want prime cuts of steak. They want all kinds of exotic vegetables. And yet, you have to decide what can you afford, and what makes sense for you. The worst steel we get today is better than the best steel was 100 years ago. We have better machine tools. We have better cutting tools. We have better design capabilities. What upsets me is when I see someone doing something foolish and I look at that wonderful chunk of steel being made into an ugly, poor performing part. To me, somebody crawled into a hole in the ground and dug out that material. They took great hazards to their health and to our environment to make that piece of steel. We owe it to that steel to make the best gear that we can.
You're here.
And within the realm of our economics, that's what we should do.
Thank you all. Are there any questions from the audience before I wrap things up here? Very good. I want to thank all of our experts for joining us today. It's been very educational, informational. If you could all help me give them a round of applause.
Thank you.
Thanks, guys.